we want to use Ampere's law to think about what the magnetic field inside of a solenoid looks like. So I've taken the solenoid and cut it in basically a cross section. So at the top of all the loops of the solenoid, I have currents that are coming out, and then correspondingly at the bottom, there's going to be the loop of wire that's carrying the current into the plane of the page. And we just sketch a few of the magnetic field lines. That is going to circulate around counterclockwise. So is that guy. So is that guy. So is that guy. We look at some of these at the bottom. Those are going to rotate around clockwise. So like that. And it's this principle of superposition that gives you the intuition for what the magnetic field is going to look like. So if I look at neighboring currents, this one is making magnetic field that's going up, while its neighbor is making magnetic field that's coming down. And so those are always like canceling out. So the up and down parts cancel out. Inside the solenoid, right, the bottom set of currents is making a magnetic field that points over to the right, and the top set of currents inside the solenoid is making a magnetic field that points over to the right. Okay, now let's look at outside. Outside, above the solenoid, all of these currents are making a magnetic field that points to the left, while all of these are still making a magnetic field that points to the right. So we wind up with B equals 0 above the solenoid, and then if we think about below the bottom row of currents, all of the top row of currents are still making a magnetic field to the right, but now all of these are making a magnetic field to the left. And those are going to cancel out. And the solenoid obviously is going to have rotational symmetry, right? So symmetry about an axis that goes through the middle of the solenoid. So it doesn't really matter that I said top or bottom. These are general statements about the magnetic field outside of the solenoid. So we have our general picture that this solenoid is going to make a magnetic field that is going to point along the axis of the solenoid from left to right due to the superposition of all of these tightly packed together currents, and the magnetic field is going to cancel out outside of the solenoid. All right, so let us make a loop we want to apply Ampere's law to. And the loop I'm going to pick is just going to encircle some of the currents. And I want my loop going to integrate along gamma that's going to go around counterclockwise. And we'll go from point A to B, B to C, C to D, and then D back to A. All right, so let's apply Ampere's law to that rectangular loop. And I'm going to set this to be a length L that is, as of right now, unspecified. All right, so I add up magnetic field, component of the magnetic field along my loop as I go around the loop, and just add all those together. So this is going to have 4 parts. There's a part going from A to B, and then in there the magnetic field is uniform. It's pointing in the same direction that I'm adding things up along my loop, and I picked that dimension to be L. Okay. also from B to C, I'm going to in principle have some contribution, but whatever that contribution is going to be undone by the contribution of going from D to A, because from B to C, I'm adding things up as I'm going up, and then from D to A, I'm going to add all the things up as I'm going down. So whatever the contribution is along here is canceled from D to A. And then the last side, as I go from C to D, it's also of length L, but there the magnetic field vanishes. So everything from the left-hand side of Ampere's law is just going to give me magnetic field strength times L. All right, so now let's think about the right-hand side of Ampere's law. Mu naught times I enclosed. Well, along this length L, I am enclosing some number of currents. So it's not just one, but that current is repeating over and over again inside my loop. And since I haven't specified a value for L, I also really haven't specified a value for N. I mean, we can sit here and count it, but for a real solenoid, this is going to be a very, very many currents very close together. So I'm going to leave this as an arbitrary statement. Some number of turns, N in the solenoid, times the current in one loop of the wire. So now we've got the left-hand side and the right-hand side of Ampere's law. And so far this is telling us B times L is going to be mu naught times N times the current. Divide both sides by L. The magnetic field inside the solenoid is uniform. I have the permeability of free space, mu naught. Big N, the number of turns over the length L, is written out as the turns ratio, N, little n. And then I have the current I. And in fact, as promised, it is uniform. No spatial dependence. As long as I am inside the solenoid, it's a constant magnetic field. And this little n, the turns ratio, is the number of turns in your solenoid divided by the total length of the solenoid.